Hello. In this short video, I will discuss an interesting property of probability density functions. This can be stated as a theorem as follows. The location of the maximum of a probability density function depends on the choice of the variable. That is, consider this probability density of a variable y, which has normal distribution with mean 1 and variance 1. Then clearly, the histogram also shows us that the mean is 1, that is the peak value of the probability density occurs at y equal to 1. But when this variable y is transformed into a new variable x, basically when this y is not when you perform a nonlinear transformation of this variable y into a new variable x, that is x equal to exponential of minus y, where this is a nonlinear transformation, and the peak value will be at a location different than exponential of minus y hat. That is, this transformation cannot be applied to the statistics of the probability densities. So in other words, the location of the maximum of a probability density function depends on the choice of the variable. So for nonlinear transformations, the peak value changes. That is, it is not same. The peak value cannot be determined by using the function, the same functional transformation of the statistics of the original variable. That means in this case, x hat is actually at 0.13. This is the distribution of the exponentially transformed the random variable y. And whereas exponential of minus y hat, that is the original mean of y, is 0.368. So which are actually completely different. But when the transformation, that is when x equal to g of y, the transformation of y to x is linear, as in this case, that is x equal to 2 times y, then the statistic mean, that is the peak value of the probability density function, can also be determined by the same transformation. That is, when the mean value of y is at 1, then the mean value of x equal to 2y is at 2. Next, we will look at the mathematical proof for this theorem. That is, consider a random variable x and its probability density px of x, and consider another variable y, which is basically related to x as follows: g of y, where g is a nonlinear function. That is, the random variable x is transformed into a new variable y. Then its corresponding probability density is p of y. Now the theorem says that the maximum value, that is the value at which p of x hat equal to 0, and the maximum value of y, that is p of y hat, equal to 0, they need not necessarily be same. That is, the theorem says that these 2 points are actually different from each other when g of y is a nonlinear transformation. That is, at this maximum value, x hat is not equal to g of y hat, but x hat is actually equal to some other value, g of y tilde. So let us look at the proof. So start with the relation between the probability density p of y and probability density p of x is actually given by this expression, that is the probability density of y is equal to probability density of x multiplied by this Jacobian factor. Jacobian. So this is the relation between the probability density of x and a probability density of a variable which is a nonlinear transform of x, or the other way around. So in order to prove the theorem, let us look at the derivatives. So the maximum of p of x occurs at, as I said, px of hat equal to 0, where x hat is the maximum. The maximum of PDF occurs at x hat. Now for the probability density p of y, and it is a function of y, the maximum occurs at d of y p of y equal to 0, which means that now by using the definition, we get dy px of g of 4 by using the original transformation and also the Jacobian factor, dx by dy equal to 0. But we know that x is equal to g of y. So this becomes derivative with respect to y Px of g of y, and this is g dash of y equals 0. Now, by using the derivative of a product, we can simply write that p dash of g of y multiplied by g dash of y into g dash of y, that means g dash of y square, plus px of g of y multiplied by g double dash of y equals 0. So it clearly shows that the value, that is at y hat, the value of this function is 0, but not px of g of y hat is not equal to 0. What this result basically says is that the maximum of p of y does not occur at y hat. Does not occur at y tilde, where x hat is related to g of y tilde. That is, y tilde is the corresponding value for the x. But when the relation is linear, that is, when x equal to g of y is just a linear transform, that is g of y equals a plus by, then x is just a linear transform of y, then we can see that the maximums occur at the, then the maximum are actually correspond to the same location, that is x hat equal to g of y hat. That is, at x hat and y hat, the derivatives of the probability densities, that is p dash of x hat is equal to 0, and similarly p dash of g of y hat, which is 0, and also p of y hat derivative is 0. This is only true for a linear transformation. This is because the derivative g dash of y equal to b and g double dash of y equal to 0. And if you insert these values in this equation, you get p of x dash g of y into b square equal to 0, because this term is already 0. Hence, at y equal to y hat, we have px dash of g of y hat, that is the derivative of the probability density function, is 0 at the peak value g of y hat. Hence, for a linear transformation, the statistics of, that is the statistic mean, the mean value, hence for a linear transformation, the mean value can be determined by using the original transformation on the mean of the y value, that is the random variable y. And to conclude, the peak of the location of the probability density function basically depends on the choice of the variable. For example, that is for nonlinear transformations, the peak of the transformed variable cannot be determined by using the same transformation on the mean of the, or location of the peak value of the original variable. Thank you.